This is IAQ Radio, Indoor Air Quality Radio, the voice of the indoor air quality industry, with your hosts, Radio Joe Hughes and the Z-Man, Cliff Zlotnick. And now, Radio Joe Hughes.
Good day and welcome to IAQ Radio Plus. It's episode 670, and this week we welcome Dr. Charlie Weschler for a discussion on ozone, hydroxyls, and the indoor environment. So what inspection and remediation pros should know. Before we get started, let's thank our sponsors. They're the reason we can continue doing the show. And don't forget, after the show, you can continue the discussion at afterthoughts.iaqradio.com, sponsored by First On Site. Our marquee sponsor is First On Site at firstonsite.com. Our association sponsors are the American Conference of Governmental Industrial Hygienists, ACGIH.org, the American Industrial Hygiene Association, AIHA.org, the Cleaning Industry Research Institute, CIRI Science.org, the Institute for Inspection, Cleaning, and Restoration Certification, IICRC.org. Industry sponsors are AEML Laboratories, AEMLINC.com, Particles Plus, ParticlesPlus.com, TSI Inc., TSI.com, Sunbelt Rentals, SunbeltRentals.com, April Air, April, AIRE.com, Healthy Indoors Magazine, HealthyIndoors.com.
And now you can win a cool prize. It's time for the IAQ Radio Trivia question. Be the first to correctly answer. Simply email your answer to czlotnick@cs.com. Or if listening live, just text your answer from your computer. And now, here's the Z-Man.
All right, no Z-Man this week, so I've got to take care of the trivia question. I want to congratulate, first of all, Victor Cafaro in Virginia, first to answer and identify pinene as a major liquid extract of conifers. This week's IAQ Radio Trivia question for July 15th, 2022 has been sponsored by TSI, an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations at tsi.com. All right, here's the question. Name the combination of terms by which hydroxyl radicals were originally called. And you can text that answer in here or send it to czlotnick@cs.com. All right, so this week we've got Dr. Charlie Weschler. After completing his PhD in chemistry at the University of Chicago in 1974 and his postdoctoral work at Northwestern, he joined Bell Laboratories' Physical Chemical Division and was made a distinguished member of the technical staff in 1986. He worked at Bell Labs and its successor institutions for 25 years. In 2001, he accepted positions at the Environmental and Occupational Health Science Institute at Rutgers University in New Jersey and at the International Center for Indoor Environment and Energy at the Technical University of Denmark. In 2010, he also joined the Building Science Department at Tsinghua University and as an ongoing visiting professor. His research interests include chemicals in indoor environments, their sources, their chemistry, and their interactions with building occupants. Welcome, Charlie. Great to see you.
Thank you, Joe. Good to be here.
Always a pleasure to get a chance to chat with you. I had a great chat before the show. Let's jump right into this whole topic of maybe get a little background on ozone and hydroxyl radicals. I know some of our listeners are more in tune to what they are and how they work, but others maybe aren't quite as aware.
Sure, Joe. I'll start by saying something about typical indoor ozone concentrations and typical indoor hydroxyl radical concentrations. And please just jump in at any point if you have questions or you want elaboration. So in a typical indoor environment, if there's no indoor source of ozone, if you're not running an ozone generator, the indoor ozone concentrations are typically 5 to 20 ppb, depending on outdoor concentrations and air change rates. The ozone that you find indoors is coming from outdoors. It's outdoor to indoor transport. At the same time, the hydroxyl radical concentrations are much, much, much lower, about 4 times 10 to the minus 6 to 4 times 10 to the minus 5 ppb. So you remember I said indoor ozone's on the order of 5 to 20 ppb. Now we're talking 4 times 10 to the minus 6 to 4 times 10 to the minus 5th. You see just how much smaller the hydroxyl radical concentrations are. Those concentrations are so small that people normally use units of molecules per cubic meter instead. So in terms of molecules per cubic meter, there's roughly 100,000 to 1 million molecules of OH per cubic meter of indoor air under typical conditions. So where is this OH indoors coming from? It's not coming from outdoors. OH is so very, very reactive that outdoor OH just doesn't make it indoors. It reacts along the way. The OH we find indoors is a consequence of indoor ozone reacting with alkenes in the gas phase. And one of the products is the hydroxyl radical. So now that we have them indoors, ozone and OH, it's important to appreciate that they react quite differently with organics in the air. Ozone is relatively limited in terms of what it reacts with. Ozone goes after compounds that have carbon-carbon double bonds. It attacks that carbon-carbon double bonds. So roughly 10% of indoor organic molecules have double bonds. But even if they have double bonds, that doesn't guarantee that ozone will react fast enough with the compound in the air to compete with air change. So an example there is isoprene. Our breath contains isoprene. It's a product of metabolism. Isoprene has 2 double bonds, but ozone reacts with isoprene relatively slowly, even though it has those 2 double bonds. So the ozone isoprene reaction is not important indoors at normal air change rates. Those molecules are swept out of the air before they have a chance to react with one another. It's only when the air change rate becomes really low that you start to see products of ozone isoprene chemistry. Now, if we turn around and we look at the hydroxyl radical, it's much, much, much more reactive than ozone. Hydroxyl radical reacts with almost every organic indoors. The hydroxyl radical, it wants to become water. It pulls hydrogen off of organic molecules. Now, when it pulls a hydrogen off of an organic molecule, it leaves a free radical. We'll call that R dot. And that free radical, typically the first reactive thing it bumps into is oxygen, molecular oxygen, O2. So that R dot reacts with O2, and now you've got alkyl peroxy radicals. And from there, all sorts of things happen. Now, I mentioned that OH is much more reactive than ozone. So let's go back to isoprene from our breath. A single OH molecule reacts with the isoprene molecule about 10 million times faster than a single ozone molecule. So as OH concentrations go up indoors, the reaction between ozone and isoprene becomes important. And that can be a source of methacrylene and methylvinyl ketone. So I like that example because anytime you have an occupied environment, you have isoprene. And the higher the occupant density, the more isoprene you have in the air. It's pretty easy to get up to about 2 ppb of isoprene. And ozone does almost nothing with that isoprene, but OH at higher concentrations can react with that isoprene. So keeping that reactivity in mind, the fact that OH is just so very, very reactive versus ozone. In indoor environments, the largest sink for indoor ozone is surface reactions. It's ozone reacting with indoor surfaces. The gas phase reactions are still important. Ozone reacts with terpenes in the gas phase. It reacts with other compounds in the gas phase. But most of the ozone is being removed by surface chemistry. In contrast, the hydroxyl radical is so reactive that it doesn't get very far before it bumps into an organic molecule and reacts. So most of the reactions for the hydroxyl radical are in the gas phase. Very few hydroxyl radicals make it all the way to a surface. What else to say there? Well, I think that provides something of an introduction to ozone versus OH indoors, where they come from, ozone from outdoors, OH from indoor ozone-initiated chemistry. The reaction rates, OH, much more reactive than ozone. Indoors, ozone lost primarily to surfaces, although some gas phase chemistry occurs. Hydroxyl radical, indoor loss, primarily to gas phase reactions, very few surface reactions.
Just as a quick follow-up from our audience, what is isoprene?
So isoprene is a product of our metabolism. It has 2 double bonds. And to see its chemical structure, I recommend you simply wiki it rather than my trying to describe it verbally. One way to think of isoprene is it's half a terpene. Okay, so you can build different terpene molecules with 2 isoprenes, if that helps.
Is it kind of like a byproduct or a metabolism, or is it?
Exactly, Joe. Exactly.
Okay.
Okay. So if you eat lunch, you'll see the isoprene levels in your breath go increased. If you stand up right now and run in place, your isoprene emissions will go up.
And is there? I'm just curious because I've never really talked much about isoprene. Are there health effects associated with too much isoprene?
No, you'd have to get up to really high concentrations. Remember, this is something that's in our lungs, that we're exhaling. So it's endogenous. What can be a concern are some of the products of isoprene oxidation. So I mentioned methacrylene, and at high concentrations, not at low concentration, but at high concentrations, methacrylene can cause eye irritation. It's what's called a lacrimator.
Interesting. All right. Let me ask about outdoors. The combination of these hydroxyls and rain has been described as Mother Nature's vacuum cleaner. But indoors we have OH, but we don't have the rain. Is that important?
Yes. I'm very glad you put it that way. It is important. Outdoors, that combination of OH and rain are cleaning the air. So why do we need that combination? OH takes these organics outdoors that might not be too water soluble to begin with, and by oxidizing them, it makes them much more water soluble, so that when it rains, the rain removes these water soluble oxidized products. So indoors, the same chemistry happens. We make the oxidation products, but without rain, those oxidation products linger in the air or sorb to indoor surfaces. So we don't have that mechanism indoors to get rid of the oxidized organics, namely rain, that we do outdoors.
Is it similar with ozone? Because I've also heard that ozone, when you have a lightning strike, you get increased ozone. Is that similar?
It's similar in the sense that those molecules outdoors that are oxidized by ozone will then be rained out during that thunderstorm. But recognize that only a subset of the outdoor molecules are oxidized by ozone, primarily those with carbon-carbon double bonds, while OH is going after everything outdoors, all of the organic molecules. OH is grabbing a hydrogen off of all those outdoor organics and oxidizing them. And when I say oxidizing, basically think of increasing the oxygen to carbon ratio in a molecule. The higher that oxygen to carbon ratio, roughly speaking, the more water soluble it's going to be.
And is there always both ozone and hydroxyls in the atmosphere, both indoors and outdoors?
Pretty much, Joe, because you always have alkenes in the atmosphere. So do you always have something for ozone? You always have compounds that have double bonds that ozone can react with. And when ozone reacts with those compounds that have double bonds, the very first thing that happens is you make something called a primary ozonide. You can picture ozone, which is 3 oxygens, attaching itself on either side of that carbon-carbon double bond. That's called a primary ozonide. And that primary ozonide is relatively short-lived, although there are such things as stabilized Kriege intermediates. We won't go into that right now. But when that primary ozonide breaks apart and gives you the Kriege intermediates, those Kriege intermediates participate in a cascade of chemistry. And one of the pathways takes you to the hydroxyl radical. So if you have indoor ozone and you have carbon-carbon double bonds indoors in the air, you're going to have hydroxyl radicals.
I've got a question from the audience. The smell when rain starts is called petrichor. What is that?
I like the word. I confess I'm not familiar with the word, but I tend to think of geosmin as the smell of coming from the earth when it's been dry and you get the beginning of a rainstorm. It comes from asphalt too sometimes, but geosmin is a sesquiterpene, and it's dry in our area of New Jersey right now, and we might have some rain tonight. And when the rain begins, you're going to get that characteristic odor, and there's numerous chemicals that are going into the air when the rain begins. But I think the dominant odorant is geosmin.
All right, now we have an audience that's interested, obviously, in how these things work in indoor environments and then the remediation of indoor environments. Let's start with this. Is ozone the same when it's produced by corona discharge or UV lights or however it's produced? Is it always the same thing?
Ozone is always ozone. O3 is O3 is O3. It's the byproducts that result. When you use UV light, you can do it in such a way that you're making only ozone. And the best way to ensure that is to use UV light and tank oxygen. Then you're going to get just ozone. But you use ozone in air, you're getting primarily ozone. UV in air, primarily ozone. When you use a corona discharge, I mean, basically that's a spark, right? You're going to get some nitrogen oxides as well. And devices can be engineered in such a way that you try to reduce the amount of nitrogen oxides you get, NO and NO2. But if you have a corona discharge, if that's how you're making ozone, you're going to get these nitrogen oxides. So basically, I'm saying with UV, you make primarily just ozone. You don't have to worry about the nitrogen oxides. When you use a corona discharge, you do have to worry about the nitrogen oxides.
And those nitrogen oxides can be important in indoor environments, although that's not typically the source I think of when I think of nitrogen oxides in indoor environments. Does that make sense?
Yes, that makes sense. And so I'll bounce a question back at you. What do you think of as a source of nitrogen oxides?
I think of combustion products.
Absolutely. Yeah.
Stove, gas stoves, things like that.
That's right. We do get outdoor to indoor transport of nitrogen oxides, and nitrogen oxides used to be much higher outdoors in urban areas than they are today. So fortunately, outdoor to indoor transport of NOx is not as important as it used to be. And you're absolutely right. Indoor combustion is an important source of NOx.
I've got another from the audience here. O3 is nearly a profane word within the EPA. Now that's the audience saying that, but it is used around the world for everything from air purification to medical treatment. Why the disconnect, do you think?
What we have to recognize is that the impact of inhaling O3 is going to depend on O3 concentration. And the first thing you think about is respiratory tract effects. And I don't know for how many years we've had chamber studies where human beings have been exposed deliberately to elevated concentrations of ozone. And one of the results is decreased lung function. That's not a good thing. Have you ever done an FEV test where you blow into the device and up goes the ping pong ball? And you can do that before an ozone exposure and then have an ozone exposure and try that again, and you're not going to get the ping pong ball as high. And fortunately, most of us have a lot of excess capacity in our lungs. But if you have COPD, reducing your lung function is not a good thing. So I think ozone was originally regulated. I'm not certain of this, but I think originally the regulations were based on those health effects. But over the years, the epidemiology showed that when outdoor ozone increased, morbidity and mortality increased. And there were both short-term effects and more recently long-term effects have been observed between increases in outdoor ozone and increases in things like hospital admissions and deaths from various outcomes. The current standard for ozone outdoors is largely based on epidemiology, these associations between increases in outdoor ozone and increases in various health ailments, including ultimately death. But this is a function of concentration, right? And the ozone in my house right now, I have the windows open. I'm guessing the ozone in here is about 15 ppb. I don't worry about ozone at 15 ppb, but I used to run a lot. And there were days when I ran and the ozone was 100 ppb outdoors, and I'd finish a run and I would feel it when I took breaths.
I've got a couple follow-ups from the audience, but before we go there, I want to kind of go back to that ozone and the chamber studies and the health issues. I'm assuming we don't have that kind of information on hydroxyls. Is that accurate?
That's accurate. That's accurate.
Why don't we?
I don't think there were the it wasn't on the radar the way ozone is on the radar. For one thing, and perhaps this is simplistic on my part, it's so difficult to measure the hydroxyl radical. We've been able to measure ozone reasonably well since the 1860s, 1870s. And when you can measure something, you pay attention to it, right? And you could see early on, you could see that ozone affected lung function. You didn't have to be an Einstein to realize if you were working in a lab with high levels of ozone, you were going to feel it. The hydroxyl radical, even today, to measure hydroxyl radical in real time, we're talking about instruments that are between $500,000 and $1 million, instruments that require sophisticated lasers and all sorts of special components. So I'd say that's part of it. And I think hydroxyl just hasn't received the attention of ozone. I think it would be quite interesting to conduct chamber studies with elevated concentrations of hydroxyl radical, but I'm not familiar with such studies.
Okay, that makes sense though. I mean, it's something that it's hard to measure. So it's hard to do studies on something you can't measure very inexpensively, I guess would be, or at all. I guess for years we couldn't even measure them very well at all. I got another follow up here. I want to, because one of the audience asked that we make sure we follow up. Does UVC fixtures produce ozone?
Yes, they can. And it's going to depend on the design of UV fixtures. And it's something that I think most manufacturers pay attention to. They try to limit the amount of ozone that's being produced. And in some cases, if you're actually passing air through a UV device, you can have a charcoal filter at the end before the air exits. And that charcoal filter can do a reasonably good job of removing any ozone you might have been produced via the UV and air.
And I just want to let the audience know we will be going into a lot more detail on UV and UVC when we come back with our part 2 of the NASEM Why Indoor Chemistry Matters shows. We've got some great guests coming on to discuss that, and I think we'll go into more detail then. But I wanted to kind of go into this hydroxyl a little more. Well, first, what piqued your interest in studying ozone and now hydroxyls and indoor environments and how they affect indoor environments?
It goes back to my Bell Labs days, and this is the early middle 80s, 1980s. And we heard about a telephone switching office in Atlanta where the insulated power cables were cracking at a much faster rate than was anticipated, and cracking faster than they were cracking in other areas of the country. And it certainly sounded like ozone, but at the time, the general assumption was that indoor ozone concentrations were negligible, that ozone was outdoors, and that when very little ozone actually made its way indoors because ozone was that reactive. I was able to purchase a couple of DeCivi ozone meters. Some of the people in your audience are probably familiar with those instruments. They were great instruments, still are. Some of them are still operating. And we took those instruments down to the Atlanta office and started making simultaneous outdoor and indoor measurements. And it was apparent that we had ozone in that office, and the indoor ozone tracked the outdoor ozone. When outdoors went up, indoors went up. When outdoors went down, indoors went down. And the office was operating on an economizer cycle. And when they were bringing in lots of outdoor air, the indoor level was a lot closer to the outdoor level. And that sparked my interest in indoor ozone. And we proceeded to make measurements in a lot of different offices and a lot of different settings, and looking at the impact of air exchange on the ratio of indoor ozone to outdoor ozone. So my interest in ozone indoors began because the impact ozone was having on the telephone switching equipment, not just the insulated power cords, but also some of the polymers that were used in devices.
I understand that prior to this week, you may not have been as familiar with what's going on in the restoration industry as you are now. And there's a lot of sales of these products. And right now, as you are aware, hydroxyl generators are sold to help with breaking down odors in indoor environments. And oftentimes, people are told that these can be used while you're in the same area working and doing your work. I understand that you may not, we don't know enough about hydroxyls at this point to make definitive statements, but does it seem, is breathing high indoor concentrations of negative air ions produced by ionizers, what do we know about that with respect to health? Do we know anything?
Not a lot. There was a study done at Tsinghua University recently, actually, by Yinping Zhang and his colleagues. I was not involved in this study. And they took advantage of the dormitories at the university. And they installed ion generators in the dorm rooms. And they measured PM 2.5, both when the ion generators were operating and when the ion generators weren't operating. And they also measured various biomarkers of oxidative stress. And this paper has been published in the journal Indoor Air. I think it was published a couple of years ago. The first author is LIU. And they found that indeed, the ion generators brought down the levels of PM 2.5. When they ran the ion generators, they saw a decrease in the amount of PM 2.5. But, and this is disturbing, the biomarkers of oxidative stress, even though the PM 2.5 was going down, the biomarkers of oxidative stress went up. So something's happening, and we don't know, we don't understand the biochemistry, why, but I think that's a cause for concern. That lights the caution light.
Gotcha. There's a follow-up. If hydroxyl radicals have such a short life, then why do we worry about them?
Because of what they make, what they can potentially make. And by the way, that last question, you were asking about ionizers. You were not asking about hydroxyl radicals, right?
Good point. Let me make sure I was reading. It's just, they were talking about negative air ions in general, I guess.
Right. So I want to make it clear that study was looking at ionizers. It wasn't looking at hydroxyl radicals. But
gotcha.
Since the question was about ions, that's what I tried to answer. So back to the hydroxyl radicals. If they are so reactive, and how reactive? I mean, their lifetimes are on the order of tens of milliseconds. In typical indoor environments, the lifetimes are maybe 10 to 50 milliseconds, so really short. But they're making things. They're making, to begin with, these alkyl peroxy radicals. And from there, alkyl peroxy radicals aren't stable. They're going to react and make other things. Some of the stable products are going to be hydroperoxides, and some of those hydroperoxides may have adverse health effects, but we really don't know well at this point what the health effects of these different oxidation products are. So if you're talking about hydroxyl radical concentrations in typical indoor environments, those presumably are safe. That's what we're living with. If you're talking about the hydroxyl radicals outdoors, and at noon in the summer, they might be an order of magnitude higher than what we have indoors. We know we can live with that. But what happens if we start talking about much higher indoor hydroxyl radical concentrations and the resulting products? I think right now we really don't know much about the potential adverse health effects.
And from what you said, it sounds like we really don't know how much hydroxyl radical this equipment is actually generating.
I know of only one study in the literature that's used state-of-the-art instruments to measure hydroxyl radicals from what this article called a commercial air cleaning device. And I sent you that article last night, I think, Joe. The first author is Fletcher, and it's from Nick Carslaw's group in England. And I thought that particular hydroxyl radical generator, that air cleaning device, was interesting. They were using the reaction of ozone and limonene to make OH. That was their source of OH. And when they were running that particular air cleaning device, the hydroxyl radical concentrations got up to about, I think I recall 10 million per cubic centimeters. I'd have to look at the article again.
Background was 100,000 to a million?
Yeah, something like that.
Okay, gotcha.
Yeah, so you were seeing an increase of 10 to 100 in background, depending on what that background was. And that's the only study I know of that has used, and they used an instrument called a phage, F-A-G-E. And I always forget what the acronym stands for, but a very, very expensive instrument. And
so this would be, at this point in time, almost impossible to measure in the field as you're doing a restoration project, as I kind of gather right here from this conversation.
Yeah, I'm afraid so, Joe. When I was at Bell in the middle 90s, and we were quite interested in in indoor OH. We had an empty office where we deliberately introduced ozone and limonene, and we measured OH in that empty office, but we did it using an integrated sampling approach, a poor man's way to measure OH. And what we got was an average OH concentration over a 24-hour sampling period. We looked at a molecule, trimethylbenzene, and we know the rate at which that molecule reacts with OH. And we injected that molecule at a known rate into the air. And we also injected a perfluorocarbon that doesn't react with OH. And we looked at the change in the ratio of trimethylbenzene to the perfluorocarbon and over time. And we used that to estimate the average OH concentration that was in that empty office because of the ozone limonene chemistry. You could do that type of measurement, but you need a lot of time, and you're just getting an average number.
And even if we knew the levels, we don't know the associated health effects.
Unfortunately, that's true.
Okay. All right. We've got to stop and thank our sponsors. I've run a little over. It's been so fascinating. I promise I will look through all these text messages here and get to them on the second half of our show with Dr. Charlie Weschler. Our marquee sponsor is First On Site, your trusted full-service disaster recovery and property restoration company at firstonsite.com. Our association sponsors are ACGIH, Advancing Careers of Professionals in Environmental Health, Industrial Hygiene, and Safety, interested in defining their science. ACGIH.org. AIHA, Healthy Workplaces, A Healthier World. AIHA.org. The Cleaning Industry Research Institute. See more deeply through science and research. CIRI science.org. The IICRC, a nonprofit standards development and certifying body for the cleaning and restoration industry, IICRC.org. Industry sponsors are AEML Laboratories, free shipping, great pricing, same-day results with no rush fee, AEMLinc.com. Particles Plus, feature-rich particle counters and air quality instrumentation. Count on us. ParticlesPlus.com. TSI Inc., an industry leader in precision instrumentation for monitoring indoor air. Learn how to expand your IAQ investigations. TSI.com. Sunbelt Rentals, availability, reliability, and ease for all your IAQ and restoration needs at sunbeltrentals.com. April Air, healthy home, April, AIRE.com. And Healthy Indoors Magazine, a free online magazine for industry professionals and consumers, healthyindoors.com. Okay, let me go back and clean up a couple comments here. One was hydroxyls per cubic centimeter or per cubic meter. I had written down per cubic meter, but I want to make sure I'm correct.
No, the numbers I was using were per cubic centimeter, Joe.
Per cubic centimeter.
And I certainly understand where it's confusing because so often we use per cubic meter. But in the case of hydroxyl radicals, we typically talk about number of molecules per cubic centimeter.
Very good. Thank you, Ken, for clearing that up for me. And thanks, Dr. Charlie. Go ahead.
Let me give you a very simple relationship when you're trying to convert parts per billion to molecules per cubic centimeter or vice versa. The conversion factor is 2.46 times 10 to the 10th. Call it 2.5 times 10 to the 10th. That's the conversion factor you can use to go back and forth between parts per billion and molecules per cubic centimeter.
With all of the known byproducts that are created from the hydroxyl generators, how can manufacturers make the claim that it is perfectly safe to use in occupied spaces?
Yeah, so I think our best aid in trying to evaluate the health effects, potential health effects of inhaling the oxidation products is the chemistry itself, and looking at the products that are known to occur when OH reacts with different organic molecules. I said the first step is pulling off a hydrogen atom. The next step is that R dot, the thing that's missing its hydrogen atom, is going to react with oxygen to give you RO2. RO2 is very reactive. It's unstable. It will most likely react with other RO2 molecules in the air, and the chemistry gets pretty complicated after that. But you get a series of oxidation products, including various peroxides, alkyl peroxides, hydroperoxides. And as you appreciate, peroxides can be quite reactive molecules. And when you inhale certain peroxides, they have the potential to contribute to oxidation stress. So in broad terms, that's the chemistry we have to worry about in terms of health effects. But different molecules are going to result in different peroxides, and different hydroperoxides have different toxicities, different health effects. And it's very complicated because we're talking about a mixture of organics to begin with. So we're going to get a mixture of these peroxides, and there's other oxidation products as well. So it's a messy issue, but I think paying attention to the chemical mechanism gives us a sense of the oxidation products that we want to think about to begin with in terms of potential toxicity.
Got it.
Let me
Okay,
follow up question.
Go ahead, John.
If you had a loss in your home, Charlie, and someone wanted to put a hydroxyl generator in there, would you stay in the house while it was running?
No, I would not, John. Just a precautionary principle.
It's a fair
And
question.
presumably, if the hydroxyl radical generator is going to do anything, it's going to take the OH levels in the home above what they are right now. But how much above? I think it's difficult to know. Just the resultant OH levels in the home when different devices are operating.
Got it. All right, getting back to the PM 2.5 question. I think it was a follow-up to when you were talking about the ion generators. And the question reads, what happens to the smaller PM, such as the PM 0.3, when the PM 2.5 is reduced?
Good question. The PM 2.5, by definition, that's airborne particles smaller than 2.5 microns aerodynamic diameter. And there's a size distribution. And we typically refer to PM 2.5 in terms of mass per unit volume. When you're operating the ion generator, you're influencing the size distribution of the submicron particles. And presumably, you're increasing the agglomeration, the rate at which the tiny guys stick to one another when they bounce into one another. And so the size distribution when you operate the ionizer is going to be driven towards larger particles within that range, smaller than 2.5 microns. You're going to increase the rate at which the particles are removed by surface deposition. So that's a crude answer to the question. It's a good question.
Okay. Let me just read here. If ionizers reduce PM 2.5 by increasing PM 2.5 to indoor surfaces, doesn't that mean that respiratory deposition is increased?
Perhaps.
A definite maybe?
A definite maybe. The deposition to indoor surfaces in this size range, PM 2.5, it's not just gravity, but it's also Brownian diffusion. And we are increasing the impact of gravity as size distribution moves towards larger particles. Our respiration, the particles that we inhale, that's what's in our breathing zone, right? And I don't think it's going to have the same effect on inhaled particles that it has on surface removal.
Okay. So there's a follow-up question as well. As you mentioned, the byproduct of hydroxyls is ROO radicals. Do these ROO radicals help improve indoor air quality?
They are going to increase the O to C ratio for the organics present indoors. You're going to have more oxidation products. The oxidation products, many of them are benign. Some of them are offensive. Some of the oxidation products will stay in the gas phase and be ventilated out of the space. But some of the oxidation products, when you increase the O to C ratio, you decrease the vapor pressure. And some of those oxidation products are going to sorb to indoor surfaces, partition to indoor surfaces. And over time, the indoor surfaces will become a reservoir for these oxidation products. And if a few of those oxidation products are irritating or offensive in terms of odor, that can become a problem.
I have a question, Charlie. Some of these machines that claim to produce hydroxyl radicals by UV light, claim that there's a reaction also with titanium dioxide panels, and something happens on the surface of that. Are you aware of any kind of interaction between OH and titanium dioxide?
So there was an area that received a lot of attention for a couple of decades called UV-PCO, photocatalytic oxidation. And photocatalytic oxidation was using TiO2 and variations on TiO2. And the idea was that you would shine UV of a certain wavelength onto the TiO2 catalyst, and you would pass air through the device over the surface of the TiO2 that was being irradiated with UV, and you would oxidize those organics. And ideally, you would oxidize the organics all the way to CO2 and water. That'd be great. Unfortunately, they don't get oxidized all the way to CO2 and water. But first of all, why is the oxidation happening when you do that? When you shine UV light of a certain wavelength on the TiO2 catalyst, you're making hydroxyl radicals. You're making them on the surface. And now the chemistry, my understanding is the chemistry is surface chemistry. It's the hydroxyl radical reacting with the organics that are passing over the surface of the catalyst. So indeed, when you irradiate TiO2 or TiO2 catalyst with UV, you make OH, but that OH tends to stay on the surface. It's not going to leave the surface and go into the air, from my understanding.
Okay, we've got another one here from the crowd. Byproducts of ozonation can create methyl cyanide, bromomethane, and formaldehyde. Can hydroxyls create these same hazardous gases?
I think the simple answer is yes. I think the pathways might be different, but many of the oxidation products you get from ozone-initiated chemistry, you can get similar oxidation products from hydroxyl radical-initiated chemistry.
I know that there's a lot of restorers on this call, and I myself personally have witnessed a haze that appears in a room where not only a hydroxyl but also ozone being produced. An entire warehouse, in fact, filled up with a haze. One I almost called the fire department. And Cliff Zlotnick calls this ultrafine particles. Do you know what he means by ultrafine particles, and what are they?
So ultrafine particles, that term typically refers to particles smaller than 100 nanometers aerodynamic diameter. So smaller than 1/10 of a micron aerodynamic diameter. When you react ozone with limonene, for example, you make ultrafine particles. And we used to observe that regularly in our work. Now, that's not saying that these different hydroxyl radical generators are always making ultrafine particles. I alluded earlier to this paper from Nick Carslaw group, where the air cleaning device produced OH using the ozone-limonene reaction. I can see in that case where you might make ultrafine particles and the concentrations might get high enough that there's a haze in the air. That's a high concentration of ultrafine particles. They're sometimes just called UFPs. As you know better than I, there's other ways to generate OH. One of them is photolysis of hydrogen peroxide. And I would not be surprised if perhaps if you're using vaporized hydrogen peroxide, you might get a haze in that case. But I've never observed this. I'm not an expert in this area. So I'm just guessing.
Would you be concerned about any adverse health reactions from breathing a cloud of ultrafine particles?
Yes, I would. Of course, it's going to depend on the chemical constituents of the particles themselves. But ultrafine particles, not only do they penetrate deep into the lung, but some of them can actually, they're small enough that they can get into our bloodstream.
Wow.
Yeah, so.
Okay, we've got another one that just came in, and the question is with regards to hydroxyls and claims made by certain manufacturers that they destroy microorganisms, molds, and viruses. But I think that's a valid question for both hydroxyls and ozone generators. I've heard that claim made for both of those devices.
I'll begin by saying again, I'm not an expert in terms of the impact on microbes, and I'm going to make my own best guess of what might be going on here. So I mentioned that hydroxyl radicals, they're so reactive that their chemistry is basically limited to the gas phase. Very few hydroxyl radicals actually make it to the surface. So if we're talking about impacting a microbe on the surface, what's going on? To me, it just doesn't seem that the hydroxyl radicals can get there in sufficient concentrations to impact a virus or bacteria. I would guess that it's products of hydroxyl radical initiated chemistry that are affecting the microbe, if indeed there's a measurable effect. So things like hydroperoxy radicals, those can reach the surface. And I wouldn't be surprised if hydroperoxy radicals, hydroperoxides, okay, I wouldn't be surprised, and those are stable products. I wouldn't be surprised if hydroperoxides could have an effect on the microbes. That's just my guess.
Yeah, but you don't know of any research that's been done down those lines.
I'm not familiar with research that's been done, but it's not my area either. So there might be research out there, and I just might not be familiar with it.
That's fair. John, you got something else?
The last question for me probably is, we're getting toward the end here.
The Roundup is brought to you by April Air, providing healthy humidity, ventilation, and air purity solutions for new and existing homes. April Air, healthy air, healthy home at apriare.com.
One of the shows I was watching with Delphine, we're talking, I understood there was some chemistry being changed, indoor chemistry, chemical reactions going on, that in fact the chemistry of the indoor environment was being changed by the introduction of these products. Can you comment on that?
If you're deliberately generating ozone indoors, or you're deliberately generating OH indoors, you'll increase the amount of oxidation chemistry that happens. In the case of ozone, you'll decrease the oxidation chemistry both in the gas phase and on surfaces. In the case of OH, you'll increase the oxidation chemistry in the gas phase, and some of the oxidation products will in turn have an impact on oxidation chemistry on surfaces. So certainly you are going to increase the chemistry occurring indoors if you deliberately increase the concentration of either of those molecules.
Great.
Would there be any health concerns about that?
The universal answer, it's a question of concentration and toxicity. So
It's not the poison, it's the dosage, right?
Devil's in the dose. Yeah.
precisely.
Yeah.
There's a couple of other oxidizing products that we use in restoration. One is the Procure, which is chlorine dioxide, which is essentially in a powdered form that's mixed with a reactant, and it creates a vapor phase oxidation treatment, I guess, is what for lack of a better word. You can also dilute it in water and spray it directly on targets. Are you familiar at all with chlorine dioxide as an oxidation method?
I'm not familiar with the product you mentioned. Okay. I do know that chlorine dioxide has been used, is used in different mitigation strategies indoors. When I look back to the concerns about anthrax, I think there were studies done to look at using chlorine dioxide to try and address indoor environments that have been deliberately contaminated with anthrax by a terrorist. There are studies of indoor materials and the products that result when they're exposed to chlorine dioxide. And those studies were led by Richard Corsi when he was at UT Austin. And his partner in those studies was Dustin Poppendieck. And there's at least one, and I think more than one paper talking about the products that result when typical indoor materials are exposed to chlorine dioxide. They had a little stainless steel chamber and they would put the materials in there. They'd introduce chlorine dioxide at elevated concentrations. They'd measure the products. So I would point you towards those two papers.
Wanted to give the last word here to Dr. Weschler, and then we'll go ahead and end the call.
Yeah.
Well, John, thanks for pinch hitting, and thanks everyone who asked questions on the chat. And I've enjoyed this opportunity to talk about OH and ozone indoors, and I think it's a fascinating topic. And the more we understand about the indoor chemistry of ozone and OH, I think the better we can answer some of these questions that you had relative to using either of these chemicals in different mitigation situations.
Great.
Thank you very much, Dr. Weschler. It was
Thanks
very
again,
informative.
Doctor.
I think we all had this eye-opening experience for a lot of us here today. Thank you so much.
For sure.
Thanks.
For IAQ Radio, I'm Spike Reel saying thanks for listening.